Hi everyone. Today we're continuing in the graph theory unit and we're going to be talking about Hamilton paths and Hamilton circuits. So in previous sections we've been interested in traversing the edges of a graph once and only once. But sometimes we're more interested in going to each vertex once and only once. For example, going over each edge once and only once might be something that a garbage man would want to do if he needs to go down every single street and pick up the garbage everywhere. But a delivery person will only need to go to a few houses in a neighborhood. So a delivery person would want the most efficient route between the houses, which would represent vertices, rather than going over every possible street, which might represent the edges of a graph. So a Hamilton path is a path that passes through each vertex of a graph once and only once. And then a Hamilton circuit is a Hamilton path that begins and ends at the same vertex. Remember, a circuit is just a path in a graph that starts and ends at the same vertex. We're going to talk about the traveling salesman problem, but before we do that, we need to find the definition of a complete graph. So a complete graph is a graph that has an edge between each pair of its vertices. So for any two vertices on the graph, there's a single edge connecting them. In this first example, we want to draw complete graphs with n equals 3, n equals 4, and then equals 5 vertices. So first, I'll draw my 3 vertices in. So we need edges to connect each vertex to every other vertex. So I'm going to label them just to make things a little clearer here. A needs to have an edge going to B and C. B needs to have an edge going to A and C. And C needs to have an edge going to A and B, which it does. So in this complete graph, we have a triangle. Now what happens when n equals 4? So let's start with A, and we'll need to draw 3 edges in to the 3 other vertices. Then B is connected to A, but needs to be connected to C and D. So there are 3 edges leaving B, and then same for C. C is connected to B, C is connected to A, and it also needs to be connected to D. Now D has one single edge to all the other vertices. So notice that we have a cross here in the middle, but this is not a vertex. That's just a place where 2 edges overlap. And n equals 5. If you want, take a second and pause your video and see if you can draw the complete graph. When we have 5 vertices, yours doesn't have to be the exact same shape as mine, just all the connections need to be the same for it to be equivalent to mine. So pause now if you want, and start back when you have your graph ready. Notice if n equals 5, the degree of each vertex will be 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then we're done. So we're going to be looking for Hamilton paths and Hamilton circuits which pass each vertex of a graph once and only once. And we're going to be focused on just complete graphs like the ones we just drew. So we have this formula that tells us the number of Hamilton circuits in a complete graph with n vertices is n minus 1 factorial. So in the next example, we want to find the number of Hamilton paths, or let's do Hamilton circuits in each of the graphs in example 1. So how many circuits are there? It's just going to be n minus 1 factorial. So if n is 3, it's going to be 2 factorial, which is 2 times 1, or just 2. When n equals 4, it's 3 factorial, which is 3 times 2 times 1, or 6. When n equals 5, the number of Hamilton circuits is going to be 5 minus 1, which is 4 factorial, or 4 times 3 times 2 times 1, or 12. So I can find 12 different circuits, Hamilton circuits, in this graph. A weighted graph is something that we haven't seen yet talking about graph theory. Sometimes we will assign numbers, which we're going to call weights, to each of the edges in a graph. So this is just an example, just a random graph put together. Maybe each of the vertices is a city, and the edges, the weights associated to them, tell us the cost of a one-way flight in between cities. Maybe it's the miles between cities that we're going to have to go. Maybe it's some other sort of cost or weight associated with them. So when we have a weighted graph, a classic problem that involves finding Hamilton circuits is called the traveling salesman problem. So let's say we have a salesman that lives in Charlotte, but they need to travel to several different cities to sell whatever it is that they're selling. We can make a weighted graph that describes the price of flights in between these cities. And then the solution to a traveling salesman problem is the Hamilton circuit in the graph, for which the sum of the weights of the edges that you travel over is a minimum. So there are a few different ways to do this. We could write down all the possible Hamilton circuits in a graph and then add up all of their weights and then see which one has the smallest sum of weights, but that is really, really tedious. So instead, we're going to use what's called the nearest neighbor method, and this doesn't always necessarily find the absolute minimum path in a graph, but it's much, much faster and will give approximately the minimum path. So if you have a gigantic network, the nearest neighbor method makes much more sense than the method that I mentioned before, which we'll call the brute force method, where you just write out every single Hamilton circuit and then calculate all of the weights. That's just too much. So the way the nearest neighbor problem works to approximate a solution, you find your starting point on the graph, and then you choose the edge with the smallest weight and go along that edge to the next vertex. And then you look at where you need to go. You're not going to go back to a city that you've been before, so you'll take the smallest edge, or the edge with the smallest weight that doesn't lead back to a vertex you've already been to. Then you just continue moving through the graph in this manner, and then when you've been to every single vertex, go back to the starting vertex however you can. Let's do an example with that. So let's say a textbook salesman lives in Charlotte, so C for Charlotte, but they need to fly to Atlanta, Boston, Daytona, and Edmonton to sell their textbooks. The complete weighted graph, which shows the price for one-way flights, is given in this graph here. We're going to use the nearest neighbor method to find an approximate solution to the traveling salesman problem. So C is our starting vertex simply because that is where the salesman lives. So it's most economical to start in the city that you live in, where you're already at, right? So this is a complete graph. So from Charlotte, he could fly anywhere. Daytona, Edmonton, Atlanta, Boston, wherever he wants to go, he could. But we're looking for a minimum weight graph for this problem. So we're going to go along the edge with the smallest weight possible. So the weights that we have as options are 75, 120, 160, and 195. So 75 is the cheapest, so it makes sense for him to start at Charlotte and then go to Daytona. And that's 75. So we started here, went to Daytona. Now where's he going to go from Daytona? 75 is the smallest, but he doesn't need to go back to Charlotte yet. He needs to go other places. So he'll go to the next smallest one that takes him somewhere he hasn't been yet. 90, 95, 85. 85 is the cheapest. So from Daytona, he'll go to Edmonton for $85. Now there are 4 options. He just came from Daytona, so he's not going to go along the cheapest edge. The next cheapest is 120. We have 2 edges that are 120, but we need to go to the one that we have not been to yet. This 120 takes us back to Charlotte, so we'll travel along this 120 to get to Atlanta. And that costs $120. Now the only place that he hasn't been yet is Boston. So even though this is one of the most expensive paths, he's just going to have to do that. And now from Boston, he needs to go back to where he started. So now the salesman has traveled to every vertex, and this should give us a minimum or close to a minimum Hamilton circuit. So the total cost we could find by adding everything up: 75 plus 85 plus 120 plus 180 plus 195 be $655. So the traveling salesman problem is the main type of problem that we're going to deal with when we're looking for Hamilton paths and circuits.